coarseness. Often we've been asking for things on the nose. Like in this formulation of the comparison test. For all n, 0 less than or equal to a sub n less than or equal to b sub n, if this series, the sum of the b sub n's converges, then this series, the sum of the a sub n's converges. When you formulate it this way, I'm asking for this inequality to hold on the nose, that a sub n be between 0 and b sub n for all n. But now we're beginning to see that we don't need to be quite so rigid. Well, one thing we've seen is that convergence depends only on the tail of the series. So something like this assumption here, for all n, 0 is less than or equal to a sub n is less than or equal to b sub n, this can be weakened. I can get away with just assuming this, that for all large values of little n, a sub n is between 0 and b sub n. And I can replace the statement that a sub n is less than b sub n with something about the limit of the ratios. I'll still make the assumption that the terms are non-negative, but instead of this inequality, I could rewrite that to just say that a sub n over b sub n, this ratio, is between 0 and 1. And the point I'm thinking about this ratio, well, I could just get rid of this, and instead of thinking about this ratio being between 0 and 1, I could just ask that the limit of this ratio be some finite value L. And at that point, I've written down one direction of the limit comparison test. So we've replaced the comparison test, which is really a pretty rigid statement, with something much more flexible. So yeah, the limit comparison test is a coarser version of just the regular old comparison test. But by coarser, I actually am claiming, this is a sort of philosophical claim, that the limit comparison test is actually better than the comparison test. And it's better for two reasons. Well, first of all, the limit comparison test is better than just a comparison test in practice, right? Beyond any sort of theoretical advantage, I mean, the limit comparison test just ends up being easier to apply. It's easier to verify this condition than it is to cook up some sequence of b sub n's which satisfy this and the sum of the b sub n's converges, say, right? This is much harder to satisfy than just some limit statement like this. Well, let's see an explicit example in practice where this really is much easier. So here's an example of a series. Let's analyze the convergence of this. The sum n goes from 1 to infinity of this fraction, n squared plus the square root of n minus n, divided by n to the fourth plus n squared minus n. Does this series converge or diverge? What I can do is build a sequence out of this. So I'm going to call the terms here a sub n, and then I'm going to look at this other sequence b sub n equals 1 over n squared, and I'm going to compute the limit of the ratio between the terms in these sequences. So what's the limit as n goes to infinity of a sub n over b sub n? Well, dividing by 1 over n is the same as just multiplying by the reciprocal. So I'm really asking about this limit. But this isn't so painful now, right? Because now I'm multiplying n squared times this. So this limit is this fraction, it's the limit of this fraction is n to the fourth plus lower order terms, n squared times n squared plus lower order things. And the denominator is the same, it's just n to the fourth plus lower order things, in this case n squared minus n. So what's this limit? Well, if I've got n to the fourth plus lower order terms divided by n to the fourth plus lower order terms, this limit ends up being 1. So the limit comparison test applies. And what I know is that this series, the sum of the b sub n's, converges because it's just a p series with p equals 2. And that means, as a result of the limit comparison test, I can then conclude that this very complicated series also converges. But it's not just that it's easier to apply, right? There's a second reason why this kind of coarse thinking is really beneficial. And the reason is that thinking this way actually gets us closer to understanding what convergence really means. Right? What's convergence all about? Well, it's certainly not about the first million terms in your series, right? Convergence only depends on the tail. And what convergence really depends on is how quickly the terms are decaying to 0. So something like the limit comparison test that asks you to look at the limit of the ratio of the terms in the series is really asking you to think about how quickly those terms are decaying to 0. And that's good, right? That means the limit comparison test isn't just a way to get the answers more easily. The limit comparison test is really showing us something about what convergence really means. And that's the goal of mathematics. The goal of mathematics isn't just answers, it's understanding. Well, think back to that example again, right? This example wasn't just answering a question. This example is demonstrating this philosophy, right? That I'm doing more than just answering the question of this series' convergence. I'm saying that there's a reason, an understandable reason why this series should converge. This series converges because it resembles in the sense of this limit between the terms in these series, but this series resembles 1 over n squared. And this p series with p equals 2 converges. So by the limit comparison test, this series does too. But that's not just a calculation, that's not just an answer. That's a reason why something that looks like this ought to converge.